Let's say a few years from now, your niece comes to your medical practice and asks you for some help with her homework. And she asks you, what is a boiling point? And so then you scratch your head and you think back to your MCAT preparation and you tell her that a boiling point is the temperature at which the vapor pressure equals the prevailing atmospheric pressure. And indeed you would be correct. But she's not quite satisfied with your response. And so she asks you, but what are the bubbles all about? You know, when you put water on a stove and you boil the water, there are bubbles. What is that? Why does that happen? You may want to pause and consider your response. Well, I recall that in first year of college, I had one of those first year college pots that sort of moved, tilted from one side to the other. And when it tilted on one side, it would boil on that side. When it tilted on the other, it would boil on that side. So obviously something is happening where the element touches the water or is closest to the water and heats the water. Something is happening at that point. Well, just like the Maxwell distribution plot, there's a certain energy that is provided to the molecules when it's closest to the heating element. And when these molecules have that energy, they rapidly expand into vapor. So the heating element vaporizes the water, turns it from liquid to gas immediately. Then the vapor will take on a shape that has the maximum volume of vapor with the minimal surface area. And that is defined as a sphere. So a sphere is created in this manner, and then objects that are most dense go to the bottom. Objects that are least dense rise to the top. And thus the vapor bubble rises to the top because it's least dense, and that's where the bubbles come from. So that is the boiling point. It is the temperature at which the vapor pressure is equal to the prevailing atmospheric pressure. Melting point. The melting point is the temperature at which solid and liquid can exist at equilibrium. The important point about the melting point is that it is pressure dependent. Some people think that ice is slippery. Well, it's not exactly true. Ice is not very slippery. In fact, people who do a lot of skating will know that just ice is not slippery. Water on ice, now that is very slippery. And what happens is that if you apply pressure to ice, you reduce the melting point. Therefore, you can actually turn the solid into liquid. More specifically, a skate is designed so that it applies a lot of pressure to a very fine area. That pressure is applied to ice. It literally melts the ice by lowering the melting point of the ice, melting it, turning a fine layer of liquid water on the ice. Now that is very slippery, and that allows the person to be able to skate without much friction. Le Chatelier's principle. Le Chatelier's principle, which is often tested on the exam, states that when a stress is applied to a system at equilibrium, the system will change in order to relieve the stress. For example, if we have this simple reaction, solid plus heat giving a liquid, well, this type of reaction would be called an endothermic reaction, meaning it's a reaction that requires heat. If this reaction, instead of requiring heat, heat was given off in the reaction, so heat would be part of the products of the reaction, then we would call that an exothermic reaction. Some people remember that if the heat exits the reaction, then it's exothermic. So this is an endothermic reaction, and so if we were to apply Le Chatelier's principle to this reaction, if we were to put more solid in this equilibrium and we were to add solid, then the stress would be solid. Then it would push the equation to the right-hand side. It would shift the equation to the right. If we were to increase the temperature, so that means giving more heat, then heat would be the stress, and therefore more liquid would be produced because there would be a shift to the right in order to relieve the stress of heat. If you were to add liquid to the equation, then liquid would be the stress, and then the equation would be shifted towards the left. And finally, if you were to decrease the temperature, so consider, if you increase the temperature, you're adding heat, it goes to the right. If you decrease temperature, then it would be the opposite, and then the equation would shift to the left. You are now looking at the phase diagram for water. In the phase diagram, we see that it is a pressure versus temperature diagram. There are three main areas in the phase diagram. They represent solid, liquid, and gas. Clearly, at very, very low temperatures, minus 100, minus 200, you're going to mostly have solid. So you take an extreme example in order to reveal for yourself what part of the graph represents what, or you just memorize it. If you look at very high temperatures, you're going to have mostly gas. The gaseous phase of water is what we often call vapor. And then in between solid and gas, we would have the area representing liquid. Any point along this part of the curve between solid and liquid is a pressure and temperature at which solid and liquid exist at equilibrium. Any point along this part of the curve is where liquid and gas would exist at equilibrium, and any point along this part of the curve is where solid and gas would exist at equilibrium. This point is where solid, liquid, and gas would exist at equilibrium, and therefore it is called the triple point. When a substance goes from solid to liquid, of course, we call that melting. From liquid to gas is vaporization. When something goes from solid to gas, that is called sublimation. When a substance goes from gas to either liquid or to solid, that is called condensation. Shortly, we're going to start looking at something called colligative properties. That's where liquids become solutions. That's when we add things to the liquid and then we see how it will be altered. These colligative properties are properties that depend on the number, not the type of molecules involved. So it could be any type of molecule, but it is the number of molecules that are going to make a difference in terms of the properties that we will be examining in solution chemistry. In fact, when you take a molecule and you add it to, for example, water, the molecule, as long as it dissolves in the water, the molecule will start to interact with the water molecules. This interaction, this new interaction, is going to change the properties of the water in many basic ways. For example, by adding the molecule into the liquid phase of the water, more water molecules are now going to have to interact with this new molecule. That means there are fewer water molecules available to enter the vapor phase because more of them are interacting with this new molecule. Because there are fewer water molecules in the vapor phase, that means in order to boil the water, you're going to have to push harder. You're going to have to provide more energy. Therefore, the boiling point will increase because there are fewer water molecules in the vapor phase. So by adding something into the liquid, and we call that something a solute into the liquid, creating a solution, right away you're going to increase the boiling point of the solution. So whatever water's boiling point was before, which is generally 100 degrees Celsius, all of a sudden the boiling point will be higher, 101 or 102, depending on the number of particles that we add to the water. Similarly, when we add this solute to water, which is called a solvent, so we add the solute to the solvent, creating a solution. Because the water molecules, again, are starting to interact with this new molecule that has been added to the water, it disrupts its ability to form crystals or the solid form. Therefore, you have to decrease the temperature even more in order to produce solid water, or the solid form of water, which is of course ice. So therefore, the boiling point is going to increase and the freezing point will be depressed. And that is a consequence of these colligative properties, adding molecules that will interact with the liquid phase. So let us look at how the graph will be altered by this. By adding a solute to the liquid, we're going to alter the graph such that the area where the liquid is will be increased. So I'm drawing arrows here because the area of the liquid is going to be expanded because the boiling point will be increased. So there's more temperature at which you have liquid solution. And the freezing point will be depressed. So there'll be more temperature again at which you will have the liquid form. Now we're going to look at some of the concentrations that we often discuss when discussing solutions. You are now looking at the units of concentration which are often used in solution chemistry. First off, we have mole fraction. Mole fraction is defined as the number of moles of a component divided by the total number of moles. Mole fraction is often symbolized by a large X. Molality. Molality is the number of moles of the solute divided by 1 kilogram of the solvent. So often the solvent in solution chemistry is water, so then we're talking divided by 1 kilogram of water. Molality is often symbolized by a small case m. Molarity. Molarity is the number of moles of the solute divided by 1 liter of solution. Molarity is often symbolized by a large m. So the number of moles of a solute per liter of solution would be something like, say, salt water. The number of moles of the solute would be how many moles of salt were placed in the water. Per liter of solution is just how many liters of salt water is present. Then there's normality. Normality is the number of equivalents of acid or base per liter of solution. Normality is normally symbolized with a large N. We'll talk about normality for a moment because often people are not as comfortable with the concept of normality. Well, first off, normality can be calculated using the equation NV is constant. That means the normality, number of equivalents of acid or base per liter of solution, times volume is a constant. That means that N1V1 is equal to N2V2. So exactly what are equivalents of acid or base? Well, we know that one of the definitions of an acid is that it can give protons. And we know that bases are proton acceptors. So we can look at a unit of acid, meaning, or equivalent of acid, meaning how many protons are dissociable, meaning how many protons can be given off by that substance. And in terms of a base, we can look at a base as how many OH minus groups it has that can be dissociated, because we know that an OH minus group, which is basic, can accept a proton. More specifically, let us look at HCl, and let's pretend HCl was 1.2 molar. So if we have 1.2 molar HCl, that means we have 1.2 moles per liter of HCl. So how many equivalents per liter do we have? What would be the normality of HCl? Well, for every mole of HCl, there is one equivalent, one hydrogen that can be dissociated. So we have one equivalent of acid per mole. This is 1.2 moles per liter. So if we multiply that by 1.2 moles per liter, well then moles cancel, and we end up getting 1.2 normal. It will be 1.2 equivalents of acid per liter. So what happens if we have 1.2 H2, so 1.2 molar H2SO4? Well, now we know we have two dissociable acid components or equivalents, and therefore we can have 1.2 moles per liter times 2 equivalents of acid per mole. The moles cancel, and we end up getting 2.4 normal. So here we look at a couple of components of acid. Examples of bases: NaOH. Clearly NaOH has one dissociable OH minus per mole, and so whatever its molarity will be, it will be equivalent to its normality. Here's calcium hydroxide, which is CaOH2. Therefore, there are two OH groups which can be dissociated, and therefore it will have, its normality will be twice as much as its molarity. So these are examples of normality, and all of this comes down to this basic equation where N1V1 will be equal to N2V2. Raoult's law helps us to numerically describe a concept which we've already discussed, and that is the idea that if you have a liquid or a pure solvent and you start to add a solute to the solvent starts to interact with the solute, and therefore the vapor pressure will be lowered because there are fewer molecules to enter the vapor phase. And so we can calculate the vapor pressure P of the solution, which is given by the mole fraction of the solvent times the vapor pressure of the solvent. So in other words, the highest number is going to be the vapor pressure of the solvent. So that was the pressure that was in the liquid before you added anything to it. Then as you start to add solute to the solvent, creating your solution, The mole fraction, which used to be 1 because it was completely solvent, slowly the mole fraction, the fraction of solvent in the solution, starts to decrease. And as this fraction starts to decrease, so too does the vapor pressure of the solution. And so Raoult's law, which is very important, helps to describe this relationship, and thus it is one of the colligative properties in solution chemistry. The next colligative properties that we will look at are boiling point elevation and freezing point depression. Given our discussion about vapor pressure and the phase diagram of water, hopefully you understand at this point why there must be a boiling point elevation and a freezing point depression. Further, the minimum is that these are expressions that must be memorized. It must be very clear in your mind that this is the way things will occur as a consequence of colligative properties. In terms of boiling point elevation, it can be calculated, and the delta T, which is the change in temperature, which will be leading to the elevation of the boiling point, is given by IBM. What an easy equation to remember. Anyway, IBM, and this time it stands for, I stands for the number of particles. B is the boiling point constant. M is the molality. It's not as if you have to memorize a boiling point constant. If it is required, it will be provided to you. The number of particles means the number of particles in that molecule, the number of particles after dissociation. M is the molality in the units moles per kilogram solvent. Some important points about this equation. To begin with, it's a delta T, change in temperature, meaning that let's say that the solvent was water, and you did your calculation and you come up with delta T, after you just plug these in, you come up with delta T is equal to 2. Great. So your delta T is equal to 2. Guaranteed on the MCAT, one of the answers will be 2. But wait, what was the question? If the question was, what will be the difference or the for the boiling point elevation, then you would be correct. It's 2. But if the question was, what is the new boiling point of the solution, then the answer certainly wouldn't be 2 degrees Celsius. The new boiling point of the solution, this only provides delta T, so you have to add the T to the 100 degrees, which we know is the boiling point of water. So the answer would be 102 degrees Celsius. And so you wouldn't choose 2 as the answer. So delta T is a very important part of the equation to understand that you have to manipulate it. And of course, the exam will also have 98 degrees to just see whether or not you thought that it was boiling point depression instead of boiling point elevation, which occurs definitively as a consequence of the colligative properties. Another important point. Let's say that we took sugar and we put some sugar in water. So we know that the sugar will dissolve in the water. And we took that water and we tried to find its new boiling point. And its new boiling point was, let's say it was 102 degrees Celsius. So, then they ask you, take the same amount of salt, the identical molality of salt, and add it to the water. What would the new boiling point be? You may want to take a moment to consider this and pause and then come back and we'll discuss it. The new boiling point would be 104 degrees Celsius. And this is the reason. The boiling point constant is constant, and it is the constant for that solvent. So we didn't change solvents, we didn't change from water to ethylene or something, so we stayed with water, so the boiling point constant remains the same. Molality, that remains the same because we said we'll take the identical quantity of salt as we did sugar. But what about the number of particles? Well, for salt, because salt is NaCl, and that dissolves into Na plus Cl minus, well, we have 2 particles. And that means that the number I for salt will be 2, whereas for sugar it was just 1. So because this becomes 2, whatever the delta T was before, now it's going to be 2 times that number. So if the delta T was 2 degrees, meaning you had a boiling point elevation from 100 to 102 degrees, so the delta T is 2, well, now the delta T will be 4, because we now have 2 particles instead of just 1. Because the delta T is 4, the new boiling point will be 104 degrees Celsius. And finally, with regards to freezing point depression, it is essentially the same equation, where we get delta T is equal to I F M, where I, again, is the number of particles, because this refers to colligative properties. F is the freezing point constant, and M the molality. Arrhenius, Bronsted, and Lowry are all scientists that essentially suggested that an acid is a proton donor, which means it can release a proton, like we looked at when we discussed normality, and that a base is a proton acceptor. The acidity or basicity of a solution can be measured from its pH. And pH is defined as the negative log of hydrogen ion concentration. Of course, this needs to be memorized, and furthermore, most questions regarding acids and bases for the MCAT exam is reduced to your understanding of the use of logarithms and the rules of logarithms. There is also the term Kw. Kw is the water dissociation constant, and it is equal to the concentration of hydrogen ions times the concentration of OH minus, which in turn is equal to 10 to the minus 14. If you were to take the negative log of all these terms, remembering that one of the rules of logarithm is that the logarithm of A times B is equal to the logarithm of A plus the logarithm of B. Remembering this and taking the negative log of each of these terms, we get negative log of Kw, so that is defined as pKw. Just like the negative log of hydrogen ion concentration is pH, negative log of Kw is pKw. So that's equal to the negative log of hydrogen. Negative log of hydrogen is just pH, plus negative log of OH minus, and that is POH. And so you see the relationship between pH and POH, because now we will develop the conversion factor for it. And that's equal to, well, it would be equal to negative log of 10 to the minus 14. Negative log of 10 to the minus 14. Based on the rules of logarithm, if you have a logarithm, and logarithm, this logarithm is base 10. If you have logarithm base 10, and you have 10 as the factor here, you have log base 10 of 10, then you can take the exponent and bring it to the front. So this is equal to 14, because we'll have a negative sign, and negative 14, so that's 14 log 10. And log 10 is equal to 1. So all this is just equal to 14. So pH plus pOH is equal to 14. That means if you're ever given the pH of a solution, you can easily calculate the pOH because you know that the sum is equal to 14. We will now calculate the pH of a strong acid. There are many strong acids. The most common ones are hydrochloric acid and H2SO4, sulfuric acid. Let us look at the dissociation of hydrochloric acid. Here's HCl and dissociating into H plus Cl minus. So it is a proton donor. It released a proton, H plus, and therefore it is an acid. What would you guess the Ka is associated with this reaction? Now a Ka is the acid dissociation constant. It is an equilibrium constant. Ka is equal to the sum the factor of H plus Cl minus over HCl. This is a classic equilibrium constant in which we have the factor of the products over the factor or whatever we have as the reactant. So products over reactants. So if you had to guess what the Ka of this was, it would be near infinity, essentially. In other words, this is such a powerful acid that essentially all of it will be dissolved into its products. And so you have an extremely high value for the products and an extremely low value for the reactant because all of it is dissolving. It's such a powerful acid. So Ka, the value of this equilibrium constant, is extremely high. So if we were given that we started the reaction with, say, 10 to the minus 3 molar of HCl. Molar, as we described before, is moles per liter, and that represents the concentration of HCl. If we were to start with 10 to the minus 3 molar of HCl, what would be the pH of solution? Well, if we start with 10 to the minus 3, because we know that our Ka is essentially infinity, meaning this will completely dissolve or dissociate, therefore we can suggest that whatever molarity we start with is going to be the molarity of each of these substances later. We start with 10 to the minus 3, then when it dissolves we will have 10 to the minus 3 molar of hydrogen ions, and we will also have 10 to the minus 3 molar of Cl minus ions. The number of moles of each don't change, because for every 1 mole of HCl, we have 1 mole of hydrogen being produced. Therefore, 10 to the minus 3 molar HCl, we will have 10 to the minus 3 molar hydrogen ions. So if we were to ask for the pH of a solution that started with 10 to the minus 3 HCl, then we would just say that pH, which is equal to negative log of hydrogen concentration, negative log, and in this situation, the hydrogen concentration we know would be 10 to the minus 3. And if we have log 10, we have log 10 base 10 to the minus 3, we bring the minus 3 to the front using our rules of logarithm. Therefore, we would have 3 log 10. And log 10 base 10 is just 1. So the pH of the solution would be 3. Just for your own interest, the pH of Pepsi or Coke is about 2. Anyway, we're going to next look at the pH of a weak acid, and we will look at how we can calculate that. We will now calculate the pH of a weak acid. There are many types of weak acids, but the classic weak acid that's given in problems is that of acetic acid. This is simply a symbol for acetic acid, since this is not exactly the chemical formula, but we will look at that closer when we look at organic chemistry. So this is the symbol for acetic acid, which is a weak acid. It happens to be an organic acid. So we know that this is a weak acid because when we look at its dissociation, acetic acid giving off a proton, our definition, one of our definitions of an acid, and producing the proton and the anion acetate. We know it is a weak acid because of its acid dissociation constant. It is not infinity or near so, as in the case of HCl or H2SO4. Rather, the acid dissociation constant is something, 1.75 times 10 to the minus 5. Now 10 to the minus 5 is obviously a very small number. You know, it's 0.00001, and so it's obviously a very small number. And because the acid dissociation constant is the product of the products divided by the product of the reactants, so that means if you have such a tiny fraction, that means you have very, very, very little product being produced. And so there is very little of this being produced. That is shown by the fact that the Ka is such a small number. That's how we know that this is a weak acid. So, if we were given a similar problem, just like the previous problem, HCl, we will use 10 to the minus 3 of acetic acid. We saw how 10 to the minus 3 of HCl would produce a pH of 3. Now let's start with 10 to the minus 3 of this substance. So the way we solve these problems is you first write what you find initially. So initially, I'll just put a little I. Initially, we have 10 to the minus 3 of acetic acid, and we have nothing of these other substances. Now note, they will rarely ask you questions in which they will have different ions in the problem. But if for whatever reason you're talking about the dissociation of acetic acid, and let's say for whatever reason they added another substance into the solution as well at the same time, something like the acetate anion, either by using sodium acetate or some other type of solution to provide this acetate anion, well then you would simply write in here whatever concentration of acetate there was. But if the solution is that of acetic acid and that is being added to solution, well then if that's the only ions that are being added, then we have 10 to the minus 3 is the initial, and then there's nothing of the others yet. Then we would look at the change. During the reaction, how will things change? Well, the acetic acid would lose some amount. Remember, it's a very small amount that is turning into the products. But nonetheless, there will be some amount X that would be lost from the 10 to the minus 3. And whatever number of moles per liter is going to be lost here, that would be the amount that would be gained here. That's similar to what we saw with the HCl. And the reason for that again is because the relationship in this equilibrium is that for every 1 mole of this, we have 1 of this and 1 of that. Had this been a problem of H2SO4, we would have seen H2SO4 and we could have seen 2 protons being given off and SO4 minus. Because the relationship between H2SO4 and the protons would be 1 to 2, then you would have twice the amount being produced. Of course, H2SO4 is not an example of a weak acid. It's an example of a strong acid. But I'm just trying to underline for you the importance of the relationship in the equilibrium. So, this one would lose X. this would gain some quantity x, and this would gain, again, some quantity x. Therefore, we write initial, the change. Therefore, at equilibrium, what do we end up with? At equilibrium, we would have 10 to the minus 3 minus x, and here we would have x, and here we would have x. So we just add up the columns. Now we want to be able to move on to calculating, well, what would the pH of the solution be? Remembering that the Ka, the acid dissociation constant, is the product of the products over the product of the reactants. Therefore, Ka, which is 1.75 times 10 to the minus 5, is equal to the product of the products, which is going to be x squared over 10 to the minus 3 minus x. So we have a component squared, we have an x, which is to the power of 1. In order to properly calculate or accurately calculate the answer for this, you would need to use the quadratic equation, which is that you'll have to dust it off from your high school memory to use the quadratic equation. However, it is very unusual to have to pull out the quadratic equation for the MCAT exam, though you are responsible to know it. So what happens in this particular problem, in order to avoid using the quadratic equation, keeping in mind that relatively little product is being formed, that means if you start off with 10 to the minus 3 and only 1 in 100,000th of this is going to be released as x, well, 10 to the minus 3 minus x is going to be essentially 10 to the minus 3. It's going to be, this number will hardly be changed because the x that is being subtracted from it is so incredibly small compared to this number. And we know that only because the Ka is such a very small number, 0.00001. So a very small amount of this is going to be given off. And because of that, we can estimate this denominator as just 10 to the minus 3. Once we've done that, now it becomes very easy to solve. It's basic algebra. We have 10 to the minus 3 in the denominator. So then, in order to bring that up, we multiply both sides by 10 to the minus 3. Therefore, 10 to the minus 3 would cancel on the right-hand side of the equation. On the left-hand side of the equation, we would have all of this times 10 to the minus 3. 10 to the minus 3 times 10 to the minus 5, well, all you do is you add the exponents. So you have 1.75 times 10 to the minus 8. That's just adding the exponents. 10 to the minus 5 times 10 to the minus 3. You add the exponents and it happens to be a negative exponent. And all this is equal to x squared. All these steps you should be able to do very quickly because you don't have a calculator, you've got other problems to solve on the exam, and so you want to be very efficient with your math. Other little tricks is that when you look at this and you have x squared, well, you want to take the square root of both sides. Taking the square root of the right side would give us x, and that is our hydrogen ion concentration is x. So we get x by taking the square root of the right side. Let's take the square root of the left side. The square root of 10 to the minus 8 is simply, it's a square root, is the same thing as the power of 1/2. And therefore the power of 1/2 would cut minus 8 into 10 to the minus 4. Now we need to take the square root of 1.75. And that is simple. The reason it is simple is that you should have memorized the squares of every number between 1 and 15, and you should be able to quickly recognize them. In other words, you should know that 15 times 15 is 225, And you should also know that 12 times 12 is 144. And that's so important for the MCAT exam because, again, you don't have a calculator. And so if you see a problem and one of the answers is 1.44, or they use the number 1.44, immediately you should be suspicious, because 1.44 suggests somewhere in your memory, hey, 144, the square root of 144 is 12. Perhaps there's going to be an equation somewhere in this problem that has to do with the square root of this number 1.44, because that makes me think of the number 1.2. So you have to consider these different manipulations. So that soon as when I see 1.75 and I have to take the square root of it, well, knowing all the squares between 1 and 15, I recognize immediately that the number 169 is a very close approximation of 1.75. And the square root of 169 is 13. Therefore, the square root, which is a close approximation of 1.75, would be 1.3. So here we have a solution with very few steps. And we have 1.3 times 10 to the minus 4, and that's X, which is our hydrogen ion concentration. So what would the hydrogen ion concentration be? Well, we would have to take the negative log of all these terms. And then we would end up with the negative log of 1.3. And then we'd have the negative log of 10 to the minus 4. Once again, minus 4 comes in front of the logarithm. And then we end up with plus 4 as our pH equals X. Therefore, we have 4 as our pH. X is actually going to be the negative log of X, which is going to be our pH. That would be more accurate. Now we would end up with 4 minus log 1.3. Again, knowing your rules of logarithms, remembering that the log of 10 is 1. The log of 1 is 0. Therefore, the log of 1.3 is some number between 0 and 1, but very close to 0. So it's much closer to 0 than it is to 1, because it's closer to the log of 1 than it is to the log of 10. So we're going to subtract a number very close to 0, so a very small fraction, from 4. In other words, just by looking at the possible answers, you would know that the pH of this solution is going to be 3 point something, very close to 4. Whether it be 3.95 or 3.9 or something, it doesn't matter. They're not, if you have to estimate, they're not going to make the answer so tight that you could not reasonably estimate. So they'll have the answers far enough apart that you could reasonably, rationally estimate. If the numbers are very tight, it means that you cannot estimate. You have to use all your significant figures. Judging from what we've already seen, the pH of an acid must be relatively low, and the pH of a base must be relatively high. This is clearly because if the pH is equal to negative log of hydrogen ion concentration, if you were to have a very small hydrogen ion concentration, for example, 10 to the minus 14 would be a tiny hydrogen ion concentration, because 10 to the minus 14 is 0.0000001, and so it's a very, very small fraction. So 10 to the minus 14, negative log of that, would give us a pH of 14. So pH of 14 is essentially basic, very basic. There's terribly small amount of hydrogen ion in that particular substance, and much more POH, which that could be calculated as well. Much more hydroxide ion concentration. And so that's one of the tricks that they have on the MCAT exam, is that they'll say, oh, this is a very strong acid, isn't it? Yes, of course. So it has a very high pH, doesn't it? The opposite. Strong acid, very low pH. So you have to have that very clear in your mind. Now let's consider that we do have an acid with its very low pH, and we start adding a base to it. A strong base, like for example, sodium hydroxide. So we're adding a strong base to our acid. Slowly the pH will begin to rise. And it will get to a point where the pH will be basic because we've added so much NaOH that the pH of the solution would be basic. Well, that is called a titration. And this is a titration curve. And this is how we're going to look at the pH of the solution as NaOH is being added. So clearly, when there's very little NaOH added, the pH of the solution would be very low. As you add a lot more sodium hydroxide, the pH of the solution gets very high. Now, there is this part in the curve, which this type of curve is called a sigmoidal curve, and there's this part in the curve where the curve sort of changes directions. The curve sort of is curved this way here, and then it's curved this way here. Sort of changes directions here. In mathematics, that's called the point of inflection. But for chemistry, this is called the equivalence point. That's the equivalence point. It's the point at which the curve changes direction. The reason why this is an important point is that this is the point at which the number of equivalents of acid and base are equal. That's the equivalence point. In fact, at the equivalence point, we get that the pH is equal to the pKa. To summarize the common things that they will ask you about on the MCAT exam for this, first, they will test to see whether or not you understand that that is the shape of a basic titration curve. And you will be able to verify that they're not pulling any tricks by looking at what was added. And if it's sodium hydroxide being added, clearly the more you add is the higher the pH. And this is the general shape of the titration curve. The other common point that they like to test is that of the equivalence point. Because once you know that this represents the pKa of the substance, because the equivalence point is where the pH is equal to the pKa, so that value would be the pKa, then you would know where the curve should be depending on what the equivalence point would be of the substance. For example, let's use a strong acid with a strong base. So we have HCl plus NaOH. So hydrogen will give off its proton. NaOH will give off its one equivalent of base. And we have this producing. So we would have H plus OH minus. That would just be water. And we have Na and Cl, that's salt. NaCl plus H2O. This is a classic reaction. In fact, many students sort of remember that if you add an acid plus a base, you get a salt and water. That's not 100% accurate, but I think the better or more general statement, and there are exceptions to it, but the more general statement to remember is that if you have an acid plus a base, you get a salt and a neutral compound. And water, of course, is an example of a neutral compound. Now, if you were to look at this and try to design, what is the pH of NaCl plus water? Well, NaCl doesn't have any hydrogen or OH minus ions, and water has an equal amount of H plus and OH minus. That according to the equilibrium constant for water dissociation. So the pH of this solution would simply be 7. So we know that the equivalence point of the curve for the titration curve of HCl for when you're adding increasing volumes of NaOH, the equivalence point would be at a pH of 7.